Hi. So I'll be talking about L1 regression using Lewis-Waite's preconditioning and stochastic gradient descent. This is with David Durfee and Saurabh Sawlani. So the problem we're considering is L1 regression. You're given a matrix A and a vector B, and you're trying to find some vector x such that ax minus b one norm is minimized. The picture looks something like this. It's a robust version of L2 regression. It can be used to solve various combinatorial problems such as shortest path and minimum cut. So we're going to call the number of rows of A n and the number of columns d. And we're specifically interested in the overdetermined case where the number of rows is much larger than the number of columns. So in this setting, we have two goals. One is we want to find an x with low relative error. So that means that ax minus b one norm is within a multiplicative factor of the optimum. And second, we want to get running times that are like of the order of n and z, number of non-zeros of A, plus a polynomial in D and 1 over epsilon. So where the O tilde hides log factors in n and D. So in particular, we don't want like polynomial in the original number of rows of A or in n and z. So those two dependencies are separate, also with the epsilons only on the D. All right, so to get these kinds of running times, you need to use something called Lewis-Waite sampling, which was developed by Cohen and Peng in 2015. Basically, it's a row sampling technique that will reduce the number of rows of A down to about d over epsilon squared, and it only takes n and z of A plus d to the omega time, where omega is the matrix multiplication constant. And I'll talk a little bit more about that later. But essentially, once you use Lewis-Waite sampling, then you can apply whatever solver you want. For instance, since L1 regression can be formulated as an LP, you can use interior point methods, which will get you running times like this with like n and z plus d to 2.5 over epsilon squared. For this talk, we're interested in stochastic gradient descent methods because they're nice in practice, and so it'd be great to get theoretical bounds for them. The previous SGD-based works was by Yang, Chow, Ray, and Mahoney in 2016, and this got a running time of n and z plus d to the 4.5 over epsilon squared. And this used Lewis-Waite's plus like a weighted version of stochastic gradient descent. So for this work, we also use Lewis-Waite's, but we add some extra preprocessing steps, so we call this whole thing Lewis-Waite's preconditioning. And then after our preconditioning step and initialization, if you just apply like basic vanilla stochastic gradient descent, you can get running times of n and z plus d cubed over epsilon squared. And if you use some tricks and accelerated stochastic gradient descent, you can get d to the 2.5 over epsilon squared. So sort of the takeaway of this is that we improved SGD-based methods by d squared and matches the best interior point methods. Also, just as a side note, if matrix multiplication takes d cubed time instead of something less than d cubed, then all of the running times for our work and the interior point method will be like n and z plus d cubed over epsilon squared. So really the Lewis-Waite's preconditioning plus vanilla SGD is the best if you're not implementing like fast matrix multiplication. With that, I'll go on to our algorithm. So it's pretty straightforward. First we do this Lewis-Waite's preconditioning, which transforms our original system of A and B into this A hat and B hat, which have lower dimensions and some nice properties. The preconditioning itself consists of a sampling and a rotation. Which again I'll talk about more later, and you get this nice property, which is that the resulting matrix A hat is isotropic and row-bounded, which ends up helping the analysis of the stochastic gradient descent. The second part is just like a simple initialization with the L2 minimizer. So we're trying to find the L1 minimizer, but the L2 minimizer is a good place to start. And then we're going to just run whatever stochastic gradient descent method you want. So first I'll talk about Lewis-Waite's row sampling. The basically the result for Lewis weights row sampling is that there's some sampling probabilities known as Lewis weights, which if you can compute these even approximately, then you can sample according to them and sample d over epsilon squared rows of your original matrix A such that your new matrix has, well, only d over epsilon squared rows. And also the L1 norms are preserved with high probability. So that's this property here. For any d-dimensional vector x, the one norm of a tilde x is within a 1 plus epsilon multiplicative factor of the one norm of ax. So this is nice because you can basically reduce your whole system to many fewer rows and then work on the reduced system. Okay, so the main algorithmic contribution of our work is this preconditioning, which again is a fairly standard thing, but we note some extra properties from it. So the preconditioning involves first sampling down A to get A tilde, and we sample by Lewis weights. And then we find some invertible matrix U such that A tilde U is in isotropic position, namely that A tilde U transpose times itself is the identity. These are both sort of standard preconditioning steps, or maybe usually the second one maybe is thought of as preconditioning. And because historically, these two steps are thought of as separate, with the sampling step thought of as like reducing the dimension, and then the rotation step thought of as like ensuring good condition number on your resulting system so that your iterative algorithms will converge quickly. So our like key observation here is that Lewis weight sampling plus the rotation in tandem will yield like some extra good properties if you sort of don't consider them as separate entities. And in particular, the good property that you get is that the resulting matrix, A hat, is isotropic and row-bounded. And so it's a pretty straightforward property. A tilde is isotropic, and also the rows are bounded. Namely, the two norms of the rows are all bounded by square root d over n. So these two properties are important for stochastic gradient descent, which I'll show in 2 slides. But first, it also helps with the initialization. So for initialization, we're trying to initialize with the L2 minimizer. So if A is isotropic row-bounded, then so this is the L2 minimizer, and then the standard. The L2 minimizer is the pseudo-inverse times B, and then since A is isotropic, the pseudo-inverse is just A transpose. So this is like really cheap to compute. So you can get this minimizer is fine to compute. Then using that, you're gonna just plug it into stochastic gradient descent. So here's like a standard stochastic gradient descent convergence. The optimality gap or expected optimality gap you get is bounded by the initial distance of your iterate to the optimal iterate, and times an upper bound on the stochastic gradients, and divided by the square root of the number of iterations. So here we also use the IRB property and our initialization, and you can get this first lemma that the initialization distance, your distance from the optimal iterate point is bounded by order square root d over n times the optimum objective value. So it's actually you actually start off very close to the optimum in this case for IRBA. And the second lemma is just that the stochastic gradients are bounded by square root n times d, so which is also a straightforward calculation. So together, you just plug that into the stochastic gradient descent equation, and you get this, so that if t is set, the number of iterations is d squared over epsilon squared, we're going to get epsilon times opt on the right, and then we have an opt on the left. So that's epsilon relative error. And each iteration takes order d times. So overall, this gives us the d cubed over epsilon squared running time for stochastic gradient descent for this problem when you use Lewis weights preconditioning. And to get the extra running time, you have to do some extra stuff. But that's up. Thank you.
Questions? No questions? All right, let's thank the speaker again. And